In this introduction to optimization, we want to understand what a general optimization statement is, name 4 different types of optimization problems, provide an example for optimal insulation thickness, and then finish with a motivating oil refining example using linear programming. So the general form of an optimization problem is the following. So this is cast as a minimization. So we're minimizing a function of x. So this function of x is known as the objective function, and x is known as the vector of decision variables. So if we only had one decision variable, we'd only have x1, but here I'm showing up to n possible decision variables. These are variables that can be adjusted until you minimize the value of that objective function. Now, we have equality constraints. These are often modeling equation, material and energy balance equations, for example, where we have a function of x, the vector is equal to 0. And this could be one equation or many different equations. Similarly, we have inequality constraints. So these can be limits to purity or some other specification. And so again, they are a function of the decision variables x. And so we have g of x is less than or equal to 0. And finally, I've listed the vector of decision variables again. So there's several types of optimization problems that you're going to encounter. One is the linear program. And the examples are typically economic decisions, blending operations, and such. Then a quadratic program includes least squares fittings. You're generally familiar with linear regression types of problems. And also model predictive control, where you're coming up with a sequence of control moves that minimize a quadratic objective function. A general nonlinear programming problem is for more complex design problems and can have any type of objective function and any type of equality and inequality constraints. And finally, we have mixed integer programs that can be either linear or nonlinear. And you encounter those more often when you have scheduling or switching. So that is, you have some discrete decisions that are on or off. Will you do this or will you do that? So a classic example of optimization problem is determining optimal insulation thickness. So we have some bare pipe that may be hot, and so you need to apply insulation around the pipe to reduce the heat loss. So one cost is the capital cost, and that's the initial installation, the cost of the insulation itself, and the cost to apply the insulation to the pipe. So although that's a one-time cost, it's typically amortized over time. So you may assume that that insulation is going to last 10 years, for example. So when you sum up the installation cost, the capital cost of the insulation, and say divide by 10 years on a simple linear example, then you'd have dollars per year for that capital cost. Then you have the operating cost, and that's the heat lost value per year. So the objective function in this particular case would be to minimize the total annualized cost. That is, you want to minimize the sum of the capital cost and the operating costs. And the decision variable in this optimization is going to be insulation thickness, because as you get thicker and thicker insulation, that's going to drive your capital cost and your installed cost up. However, it's going to reduce your heat loss as you get thicker and thicker insulation. So there's going to be some optimal intermediate insulation thickness value. And so here is a classic curve. And so notice on the x-axis, we have insulation thickness. That's our decision variable. We have the cost of energy being lost. The heat loss goes down as you increase the insulation thickness. However, the cost of insulation goes up as you increase the insulation thickness. And so it's the sum of those two costs that's the total cost, the heat loss plus the cost of insulation. So you can see by viewing that curve, there actually is some minimum of the cost on an annualized basis. So what you want to do is find the insulation thickness that gives you that minimum cost. So again, that is an outcome of an optimization statement that I'm going to minimize the total cost by adjusting the insulation thickness. Linear programming problems are commonly used to solve economic problems. So one example is crude oil purchasing. Now, here's a pretty complex diagram. This is showing the average product yield from a barrel of crude oil. So a barrel of crude oil is 42 gallons, and it goes through a lot of processing in a petroleum refinery. It gets put into different possible products that I've shown encircled in red. In general, we produce almost 50% of that crude is produced into gasoline, but a certain amount into fuel oil, heavy resid, or asphalt. Some of the kerosene can actually be sold directly. So the real question is, since different crudes have different yields, that is, a heavy crude may produce less gasoline, but more fuel oil and asphalt, how do you decide what mix of crudes to purchase? You may want to mix a couple of different crude oils to get a different product slate. And so that's shown in this slide. And notice the prices I'm showing here are roughly about 1/2 of the current prices. But I'm showing two different possible crude oils that we can bring in and process in this refinery. So crude oil 1 is more expensive, and it costs $24 per barrel. And crude oil 2 is cheaper, it's $15 per barrel. Now the problem is they're going to have different splits that I haven't shown here into these various products. So typically the more expensive crude oil may be used to produce the higher value product, gasoline, but there's going to be a certain amount of it that will go into kerosene, fuel oil, and resid. And they all have different values. So since crude oil 1 and crude oil 2 are going to yield different product splits, how do we decide the amounts of each crude to purchase? And the optimization problem is the following, in that we want to maximize the net revenue. So that is, we want to maximize the value of the products minus the cost of the oil minus the cost of refining. Each of those two crudes may have a different actual cost of refining. And so this results in a linear program, an LP, and that's going to be the subject of the next screencast. So to summarize, we give a concise review of optimization. It's important for you to understand what an objective function is, what the decision variables are, what constraints are. There's 4 classic types of optimization problems: the LP, QP, NLP, and the mixed integer or nonlinear program. We did an optimal insulation thickness example and then presented a crude oil example.